Uh, Welcome to the 14th lecture, and we are discussing about how to find out B distribution, flux density distribution along the air gap of a machine. This is our machine. On this stator there is a pair of two conductors, that means a single coil. At the back they are connected in series, and you are passing current cross dot like this, and I know lines of forces will be going like this, indicating that this surface, this to this will become a south pole and this to this will become NS, that is inside this will be NS, inside this SS. And if you cut it here and imagine you have separated it out, made it flat, then this, from this you will get this, and all the things here, this is 1 dashed. So, 1 dashed 1, and this is the air gap AG. Suppose the length of the air gap is LG. Okay. Now, to find out the B distribution along the air gap, we will make first one realistic assumptions. One is this, that the permeability of iron, that is mu r of iron part is very large, compared to air. For air, mu r is 1 air, we assume approximately 1. So, mu r of iron is very high, and I will neglect saturation, okay, and linearity is assumed. These are the two assumptions I make. Now, to find out the field around a conductor, what we apply is known as Ampere circuital law. Which you know is mathematically written as H dot dl over a closed path is equal to current enclosed by the path. And B and H are related by this, B is equal to mu 0 mu r into H. This is the thing. If you must have undergone courses and know how to analyze a magnetic circuit, I will just in view of this, what is the implication of that, I will quickly tell, then come back to this problem once again. Suppose you have a magnetic circuit like this, and here is some number of turns N, and this is I, and I want to find out the field here, and suppose there is an air gap in this of length L g. Now, if this permeability of iron is very large compared to the air gap permeability, which is 1, and it is a series magnetic circuit, mind you. So, this circuit can be written as plus minus N I. This also comes from your Ampere circuital law application, and there are two reluctances. One is due to iron, another is due to gap. These two are in series because same flux flows through both of them. Now, what I am telling, the implication of the term that mu var of iron is very large, means reluctance of iron is much higher than R g gap. Therefore, all the MMF will be dropped across air gap under such a condition. You can assume that two resistances, reluctance of iron is very small. Thank you. Reluctance of iron is very small than gap. Gap reactance is very high, although gap length is small, but because of the fact that its permeability value is so small, 4 pi into 10 to the power minus 7, and this will be 10,000 mu var values, 5,000 of the order of 1000. So, reluctance of the gap is very high. Imagine a circuit having a low resistance and high resistance in series and connected to a source. Since they are connected in series, current will be same. Therefore, what will be the current in the circuit? All the voltage will appear across the high resistance. Similarly, you can assume that all the MMF will be dropped across R g. In such a scenario, if R g is many times higher than R I, you simply divide this total MMF by R g and you can quickly get what is the flux produced, MMF by reluctance. Strictly speaking, this flux will be MMF by reluctance of iron plus reluctance of gap. But reluctance of gap is very high compared to R I. So, whether you add R I or not, it is simply like this. That is the meaning of that assumption. So, all the MMFs will be dropped across the air gap. Now, we will apply Ampere's circuital law here. So, once again I draw slightly neatly, so that this is suppose one slot, this is another slot, this is suppose 1 dashed and this is suppose 1, this is the outer stator rim circumference, this is all iron, and on the rotor I have not assumed any coils. There may be coils, but that is de-energized, but I am showing the air gap at a larger scale, it is much smaller. So, this is rotor, below this is rotor iron. The developed diagram view is this, and iron of rotor and stator, they are very high compared to, I mean mu var of rotor iron, stator iron are very high compared to the air gap, and this is your air gap. Now, suppose I want to find out the and this current direction is also known to me. This is cross, this is dot. Now, suppose I want to find out what is the value of H. The plan is like this. At this point in space, you want to find out the value of H at a given point in space. Suppose I want to find out here. Now, you see around this point, I have a lines of force. Consider a lines of force here. Okay. So, H, suppose the value of the gap H is H. So, H into L g, H dot d l I have to do. So, H dot d l becomes H into length, because along that direction only I am going. So, H g into L g plus H I into this L I stator plus H g into another L g plus H iron into L iron up to this. but these two drops are neglected, that is the meaning of that mu r. So, the integral h dot d l along any closed path, that is what I have chosen, and I have taken everything h g l g, and if you like I will write this h iron stator, whatever is this length L iron stator plus H iron rotor, L iron rotor, that is this length is L iron, and this must be equal to the current enclosed. What is the current enclosed? It is I. Okay. But I am telling these two terms can be neglected. We will always assume iron is very good type of iron we are using with respect to air gap. It does not require that, it physically means that it requires very little MMF to create a flux in the iron. Most of the MMFs will be dropped in the air gap. So, ultimately what you will get is 2 HGLG is equal to I, and I will say Hg is equal to I by 2 Lg, that is the thing. So, at a given distance from this point, say x, this is the field. What about at this point? At this point, what is the value of H? Oh, you then consider another lines of force here. And repeat this calculation HGLG, but once again current enclosed is same. Therefore, the value of Hg at any point from this to this will remain constant. Similarly, the value of Hg, if you calculate for this point, that will also remain same, is not. Therefore, this value of H at this point will remain constant. In other words, I will spoil this paper, because to be consistent with the direction. Suppose now this is the distance, wherever you choose your origin you choose. Suppose you choose your origin here, x equal to 0, this is x axis. Then I will say between this and this point, the value of H will be like this. After this cross, what is there? You will, because it is a rotating machine, you will eventually once again 1 dash will appear here, dot. But the direction of, if it is south pole here, which I have shown by positive here in this plot, what is this strength? This is this Hg, I by 2 Lg. But between this to this, it will be negative. Are you getting? From this to this, it will be negative, because sense has changed, it has become north pole. So, this is how we can show. Now, the slightly disturbing point is here, that what happens in this zone. Okay, we do not care. What people do is this, up to this point it is like this, then at the center of this slot, and it is done there. In fact, at this point I would like to tell in this way that this is a coil, I told you, listen carefully, this is a single coil. How many turns this coil is having? Only one turn. I can make a coil having multiple turns. single coil I will make. Suppose these are the two slots, you take a single piece of wire, long piece of wire, you start winding like this, you go this way, at the back you come back, draw that wire. So, by doing this you will get say 1-1 sort of thing, but here you do not stop. Once again take that wire, push it once again through this slot at the back. So, another, bring it down, another, bring it down, and ultimately of course, you will get two turns, two terminals available to you, 1 dashed. Have you, is the picture clear? You take a long piece of wire, one wire only, you push it in, at the back you go, then draw to through this designated return slot of that coil, and then repeat this once again, do not stop here, once again push it in, at the back come. So, it looks like this, go there, come out to through this slot, once again come here, bring it back, I mean draw firm line, how does it matter. Come out here, and suppose I stop here. So, this will be my 1 dashed 1. So, it will be a coil of two turn coil. In fact, in machines multi-turn coils are used, because BLV is the voltage, and when these things move in B, all these conductors will have BLV, and they will be added up. So, large voltage you can get. Therefore, it is multi-turn coil. Therefore, in a situation when there is multi-turn coil, each slot suppose is having n turns like this. Therefore, as this point I was telling that discontinuity point, what is happening is this, between there is no problem in estimating correctly if these are all cross current or dot current. This is the lines of force, that is fine, H dot d L equal to current enclosed. Now, if you choose a suppose it is a multi-turn coil like this, and if you choose a lines of force like this, then H dot d L will be the current enclosed here, not all the things, it will be slightly lesser. So, what happens, correct sketching perhaps will be like this, it is constant here, then it decreases here, and then this one, that is taking into account each current crossed and deleting those currents. So, instead of that, what people do, that discontinuity you forget, at the center of this slot make the change, that is how you show the H distribution. It is after all from positive value going to negative value along the distance. So, this one, whether it is doing slightly like this, because the slot width is much smaller compared to the pole pitch of the machine. Therefore, the H distribution of a multi-turn coil like this, if I finally sketch it, let us repeat that, it is nice. This is this, this is this, this is stator iron, here number of turns are there, all are connected in series, and all the conductors in a particular slot will either carry dot or cross current. So, suppose this is dot, all the conductors here carrying cross current. Then the H distribution here, this is LG, air gap length, iron length does not matter, stator iron, stator iron, this is the outer thing, not this is LG, stator iron, and this is air gap. I have shown in a larger scale, it is much smaller like this. Or let us show, this is the rotor iron, this is the air gap, understood. Then what I am telling, the MMF distribution, draw a line at the center of the slot and it will be like this, rectangular shaped, and it repeats. This is the H distribution. In the air gap, how much is the value of H at this point, at this point, at this point? And if you know H, what is the value of B? Just multiply that H with B. So, H g will be equal to N I by twice L g. There are two air gaps in series, and then I say B g will be equal to only mu 0. In the air gap, I want to find out the flux density. So, this will be N I by 2 L g. So, this is the shape of H, multiply it with mu 0. In some other scale, this curve is also B. So, this will be the air gap distribution of the flux density wave, constant over 1 pole pitch, constant value of B, so much Weber per meter square. And if you say that this is lines of force entering the south pole, if you assign this to be north pole, then this must be south and so on, reverse. So, this is south pole, it will be cross, lines of force will be entering like this. So, south north, south north. So, this is how a single coil, you must understand what is happening in a single coil. First, in a single conductor, then each time we will not go to a single conductor, single coil. Single coil will be the elemental thing. In any rotating electrical machines, there will be several coils, we will see in a few lectures from now. But remember, each of those coils, suppose belonging to stator structure, will be identical. Similarly, each turn, each coil on the rotor body will be also identical. What is the difference? Difference is one coil is displaced in space by some angle, that is all. Therefore, in course of time, whatever is happening to one coil, same thing is going to happen to other coils. Therefore, it is essential if you know what is happening to a single coil. So, a single coil has produced a flux distribution like this. Now, at this stage, let me tell you, suppose this is the stator of this one and it produces field like this. Now, I want to generate AC voltage. So, what I will do? I will on the rotor surface, I will put suppose one conductor, that is here. Suppose you put a conductor, a slot is there, you put a one coil and drive this conductor, open circuit, rotor is open circuit. Therefore, is not it same as the thing we started with, that is there are south north pole patterns like this and a conductor is moving. And if this conductor moves, there will be voltage across the two ends of the conductor. And what will be the pattern of this voltage? Same as this south north pattern. Whatever is the pattern of B, that will be the voltage pattern as well. Only thing, this space will be replaced by some V t, velocity into time, thereby time will come. So, with respect to time, you will get a square wave voltage for such a machine which is having on the stator a multi-turn coil carrying some current, its field distribution will be rectangular and you have a single conductor placed on the rotor surface, and suppose by some external agency it is moved in this direction, then this thing is this thing, and the value of the voltage induced here is BLV, LV constant. Therefore, whatever is the nature of B, that will be traced by the induced voltage pattern. But the irony of all these things is this, because you know by this time, all of us know that our voltage, whatever is available in your power point here and there plug, that is AC voltage. Only this, it is AC voltage no doubt, but it is not a sinusoidal voltage. Sinusoidal AC voltage we say na 220 volt 50 hertz supply. It means that it is a sinusoidally time varying voltage with peak value 220 into root 2. But here if you have a generator like this, you can only say okay, it is AC voltage, but it is a square wave voltage with some plus fixed value, negative fixed value in the one half cycle and in the next half cycle. But you would like to generate AC, then the question is how that AC voltage is generated, sinusoidal voltage. So, the answer to this question I can give, you also can give. You will say that to generate AC voltage in this conductor, your B distribution must be sinusoidal, then only BLV, LV constant. If B is sinusoidally distributed, then you will be ensured about sinusoidal induced voltage. Otherwise, in general, whatever is the nature of B, under which relative to that B distribution, if a conductor is moving, you will get a voltage induced which will vary with time. The shape of that voltage waveform against time will be same as the distribution of B along the distance. For example, this waveform, for example, you know Fourier series, I can Fourier analyze this and get a fundamental sinusoidal with lot of harmonics. One good thing is higher order harmonics, they will have reduced amplitude. So, you can say that okay, it is a square wave, but it has got a strong fundamental sine wave with lot of odd harmonics. And the idea is whether this B cannot be made a very nice sine wave smooth like this. What can be done is that an approximation to this sine wave we will try to get, and that I will discuss in the next class. Thank you.